And Linja is an overachiever and is giving 2 talks, so one of which is in the parallel session, so she won't be here, but everyone else coming down. Yeah, Shuai, are you online?
This is
Oh, yes. Let me turn on my camera.
Yeah, so Shuai, I showed this picture from Carl's lab, and he has lots of equivalent things. It'd be pretty interesting to for you to model his before and after vacuum desiccation, because that's pretty definitively water coming out of that sample, and what's left over is purely hydroxyl. So just a suggestion, because the data already exists.
Oh, that's cool. But I'm not sure whether that's exceeded the limit. So it's like if it's less than 100 ppm, I think it's hard to.
It's
It's
more.
hard to. It's more.
Remarkable bands. Is this on? Remarkable band's pretty deep. Yeah, we even see a 1.9 micron feature for
Oh, great. Yeah. Let me test it. Yeah, sounds good. Thank you.
All right, what other questions do we have? And James, I'm going to move away from the computer, but let us know if there's questions online as well.
Yeah, no questions thus far.
Yeah, I just have a comment for Parvati. You mentioned the ionosphere. There's a recent paper by Poppy et al. Where they modeled the ionosphere as a function of exospheric density, and as the exosphere gets more dense. Really interesting.
Yeah, thanks, Rosemary. That is a really interesting paper. And I am planning to talk to Andrew about this at some point. All right, we'll have one more in the room.
Hi, my question is for Marie. I was wondering if you had your choice of test bed for your camera, what kind of test bed would you build based on your lessons learned from your experiments?
Yeah, great question. We definitely need something that fits the field of view of the camera that we want to take, so that we can really think about making sure that light isn't reflecting in those ways. So there's one place that I've really would like to eventually get some funding to go to, and that's a permafrost cave in Alaska. And that is somewhere that has a lot of different cryolithologies, and you can actually start to do a sort of a CONOP study with that and do different imaging of different types of these materials in the natural environment. And in a cave, it's really nice because sometimes they'll turn the lights off for you. And so you can start to play with that. But I know that there's some other really large lighting labs they're starting to develop in preparation for Artemis. So it'd be really interesting to start to work towards doing something in there.
Yeah, Micah Scheibel, NASA Goddard. I had a question for Abigail and Paul, maybe. I was wondering if you'd be willing to speculate on where all that extra water is coming from, or if it could be something that's not water, something that we just haven't thought of yet.
Right. And so, yeah, I mean, trying to think of new things is one of the things that we're trying to do, I guess. But I mean, Paul kind of alluded to like, okay, maybe there's stuff that's deeper in the regolith. I don't know why it would preferentially go deeper versus coming out. So that's something we've talked about, but it hasn't really turned into like it doesn't feel like physical in terms of trying to figure out how it would work. Do you want to say something, Paul?
Yeah, I mean, there have been suggestions that somehow what we're seeing is migration inside the regolith itself. So somehow it's coming in and out of the optical sensing depths. No one suggested a mechanism how you prevent it from getting in the exosphere. I mean, the back of the envelope calculations are so many orders of magnitude off of what Laddie measured and placed that you would a tiny bit of leakage and you'd still overwhelm the sensor. So somebody in the audience is going to have a bright idea, and we're all going to slap our foreheads and say, God, that was so obvious. Why didn't we think of it?
But we don't have it yet.
Yeah.
Can I ask a probably not very insightful question? It was not in very good thermal equilibrium coming right outside of going into a eclipse, right? So could some weird thermal gradient
Yeah.
that's not being modeled correctly potentially cause that? Because that reflected light and then weird thermal gradient for emitted light.
Yeah.
There's something there.
Yeah, that's one of the questions we've been asking. One of the things that bothers me about that a little bit is I feel like we've seen the most change at the lowest temperatures. So whenever I think about like thermal infill, weird thermal gradients and things like that, it definitely could be something, but we also like, it weirds me out that I'm seeing more change at lower temperatures than at higher temperatures. And we do have out to 4 microns to fit temperature, which, you know, if there's a gradient, maybe that's also not looking quite at the same layer or something. So yeah, that's definitely a conversation we've been having.
All right, Dana Hurley from APL. Callum, I don't know a whole lot about GPR, but from what I've heard, it's hard to distinguish between different things that are causing the signals. What are your comments on that and your particular instrument and ability to like distinguish ice?
Yeah, no, great point. So the challenge there is the dielectric permittivity of both ice and regolith. They're very similar. So I was quite surprised actually that we were able to detect those samples even at that low concentration. So we're still kind of scratching our heads and trying to dive into the data to see what is actually showing up in that, whether or not it's a difference in the dielectric, whether or not it's something to do with scattering. I mean, that sensor can do quite a lot of different things, and they kind of bring a lot of it in with their algorithm, which unfortunately I don't have access to right now because of ITAR and some other restrictions. So we're still working on this, but I'm very interested to see kind of how they're able to detect where those were. Also point out we did, so we put in samples that just had regolith with no ice in it. We put in samples with water as well to try and see the difference between them, and it was pretty consistent throughout. So it's yeah, it's an open question at this point.
So like if there were rocks, would they appear different than chunks of ice?
Correct.
Yeah.
We looked at that as well, and voids and some other, there's a whole bunch of stuff we worked on, which is interesting. But yeah, I hope to publish on this at some point once I can get the folks at Lawrence Livermore to chit chat a little bit more about the nuts and bolts of it. So
Can I pile on to that? Really related. Have you put any like small craters or anything into like those kinds of structures? Do those mess anything up for you?
I have not looked at that. Most of the tests we ran, we buried the samples anywhere from 2 feet to a feet deep, and then just kind of covered it up with no real lunar texture involved. But that's something that we thought about doing as well, as looking at putting in a mock crater, which we've done in the other test beds, and then trying to see. So that could be interesting as well.
Cool.
To see. Yep.
Okay, I think this is for Paul, but it could be for a number of people, and it also could just be completely wrong too. So I was intrigued. Okay, so Paul was giving his talk, and he very briefly showed showed the 6 micron band in a number of different asteroids. One of them was Calliope, and Calliope is an M type, so it's the same as Psyche that we're going to do. So it's presumably metal rich, right? And there's been a lot of debate on the Psyche team about, are we looking at contamination from the rest of the asteroid belt, carbonaceous chondrites hitting, or is that something indigenous to the body itself? But it got me wondering a little bit about all these signatures we're seeing on the moon. A lot of this, is transient, right? So it can't really be carbonaceous material, but we know carbonaceous material is falling on the moon from impactors. Some of them could be low velocity. Could that be a component if you need like a deeper source mixed into the regolith in some fashion?
I haven't thought about that, Bill, but that's a good, I mean, we have 1% carbonaceous chondrite material in general in
exactly.
regolith. As far as the asteroids, that would be a good source for that 6 micron band. And in fact, I think there's a really good Spitzer spectrum of Psyche that shows a strong 3 micron band.
Yeah.
And that's probably, you're looking at that carbonaceous chondrite. Well, that's seems the Vesta lesson.
Well, we'll actually find out, I think.
Yeah.
That's but you're right. It could be, although it's not it's okay. We could talk about Psyche all day, and that might bore everybody in the audience. But it is an issue that there is all this carbonaceous material added. And so I don't know how that plays a role in anything you're seeing. And a lot of that, I think when it hits, probably loses most of its water, but it is still something I'm puzzled about. 'Cause not everything hits at high velocity. So
Yeah, some fraction of the impactor is retained. There was some
Yeah.
experiments by Tarek Dali at the gun, and his experiment showed as much as 30% of impactor water can be returned in the target, and retain, and it shows a 6 micron net.
yes. Okay, thanks.
Talking about Psyche, Stephanie Jarmock just had a paper accepted, and I think it's PSJ with JWST observations of Psyche looking at the 6 micron band, and they don't see any 6 micron band.
Well, maybe that mission can be canceled too.
Can I ask a question? Sorry, I have a question for Marie. So 2 questions actually. For your camera, like say in future astronaut will bring the camera to the surface, do you have like a standard like for like either grayscale or color bars? Like, you can calibrate your camera to see the variation in the surface color.
Yeah, they are gonna have some sample numbers and stuff they're gonna be able to put down. But for this camera, they don't have and so they'll get a little bit of color calibration, a scale within there, but not like a full out color calibration target for this camera right now, because technically it's not a science camera at the moment. So
Okay, so in PSR, are they going to use their own lasers?
that's still up for debate, and so I will leave that one. But for some of the analog tests, they used a couple of different lighting environments, including lights on the suits and lamps that they can carry with them, and then potentially cart lights. So this is still a lot of that is in flux at the moment, and so now's the time to start practicing and figuring this stuff out.
Okay, thank you.
Ishwai already knows this, but the ShadowCam team has shown that in the PSRs, it's pretty bright. It's like the lighting in this room. So that camera will be totally capable of taking good imagery.
Yeah, one thing with that is it will be able to take good imagery, but we might actually struggle with some of the textures that you're going to see on the surface, because you're going to get that light coming in from all the different angles. And so when we're thinking about different cryostructures, that may give us some information about the interaction between the ice and the regolith, then we're going to have to think a lot more about the different ways that we choose to make those images different, sort of like a structure from motion or something like that to really capture that.
Yeah, it will be also interesting to see colors. So it's like hematite. You may see something like very red or something like that.
Great.
So question for James. So I don't think a lot about sulfur, so this might be a naive question. Is there any, are there any remote sensing data sets that might be useful at kind of getting to the root of that? And if not, or maybe in addition, in terms of samples, like would Artemis 3 return samples that are useful to that, or do you really need to go to a volcanic region or the Maria?
So yeah, that's a great question. I think remote sensing techniques, it's a bit difficult to characterize at least the triple sulfur isotope or quadruple sulfur isotope composition just because of the low abundance. But there has been a paper recently published by Kathleen DeClear using I think more or less remote sensing techniques, looking at eruptions, I think on Io, and characterizing the sulfur isotope composition. But that's an active event right now. So, but I don't necessarily, to your second question, I don't necessarily need to go to volcanic deposits. In terms of Artemis 3, one of the aspects of that work I'd be really interested in is analyzing sulfur in a core that's taken in that region. So, considering that it is a cold trapping region, as sulfur is volatilized during, say, micrometeorite impacts, space weathering events, a decent amount of that sulfur, at least as sulfur particles, will travel towards the poles and be captured there. And if it does interact with UV during that travel, it'll then capture the Cap 33 and then be transferred and deposited in that surface. So if you look at a core, you might be able to determine the evolution of the lunar atmosphere or any sort of atmospheric chemistry through time as all of that sulfur is trapped in the cold trapping region. Yeah.
Thanks. That's super interesting. And if I can ask a follow-up question. So that picture you painted of sulfur migrating to the poles, do we know if it would migrate as sulfur or would it be like SO2 or some other sulfur-bearing species?
So SO2 would be really exciting because that would mean we have a more oxidized mantle source or something than the moon, but it'll probably, I mean, it's going to be originally as H2S. I mean, I don't fully know if there will be free sulfur just in gas phase kind of flying across. It'll probably be as H2S. And so some of that H that is then at the poles could be linked to some of the sulfur that was released from various sources. So we can begin to fingerprint potentially where that material came from, how processed it was through maturation events prior to delivery to the poles. And so, we often think about different elements kind of in a vacuum and singular. There's a lot of talks focusing specifically on hydrogen, but the delivery of the hydrogen and its origin and distribution can be better characterized by having parallel analyses like sulfur isotopes that can tell you about the history of that hydrogen before it was at the poles. If it was deposited there and didn't go anywhere, or if it came from somewhere else, such as the lunar mantle.
Okay, comment on that very quickly. I mean, if there is free sulfur that lands on a grain where there's adsorbed water and UV around, you very likely can form SO, maybe not SO2. SO is pretty absorptive, so there'd be no reason not to expect a potentially weak 4 micron signature due to the S double bond O effect and also UV signature. I mean, this would be something that Viper would have been able to test with its mass spectrometer, be able to sense if there is some SO there.
Sorry, I missed what the argument was. You said if there's SO2, you could see it? Something like that?
On O, one can see it with a 4 micron, 4.05 micron feature. Yes, doesn't have to be SO2. You can also see it in the UV as well.
Mm-hmm.
What other questions do we have? We have time for maybe one last question. And James, let us know if there's something online. And thanks to the folks online for staying up with us.
So sure. I guess, Carl, I'd ask you a question. You mentioned during your talk that you expected primordial ice to be more comminuted block ice. I guess I've thought a lot about the transport of water vapor to the poles, and I was kind of just wondering why you think it would be ice grains as opposed to ice coatings.
Ice coating, ice grains, as long as they're large enough, I really don't care which one they are.
Yeah, okay.
I naively perhaps assume that primordial ice, we talk about blocks, they're deep broken up. However, to your point, Cabeus, the impact of Cabeus crater, they model that as porous ice, particulate porous ice, a couple meters down. So, maybe it is hard to tell the difference between frost and porous ice, but I would still say frost is an order of a few microns in grain size. Porous ice most likely is going to be larger than that. So we should still be able to see a difference.
Okay.
Can I comment on that? So like based on the orbital data, like MCube data, we see like a slight shift for the 1.5 micron absorption feature. We think that's possible. Still not conclusive to say. That's due to the condensation of vapor phase to form those low density ice. Yeah, so that's just the information inferred from the absorption feature.
All right. On that note, I think we'll wrap things up, but it's only Tuesday, so please continue the discussions and I don't know if anyone from the organizing team is here, but it looks like the next thing on the agenda for today, so we have the public lecture. Robin Canup is talking on the origin of the moon at 7 p.m. in the Graham Chapel, and I believe, that will also be available via Zoom. No idea where the Graham Chapel is, so we'll figure it out. But thanks everyone. Thanks James, Shuai. Thanks everyone online.
Thank you.